Hi, Mike O'Malley, CPA and Business Appraiser. In this short course, I'm going to explain the basic concepts, formulas, and applications of present value and compound interest computations. Let's begin with interest calculations. Let's suppose you open a bank account and you deposit $5,000 today. We call this $5,000 the principal or present value. The compounding rate or period defines how frequently the bank will credit your account for interest earned. In the formulas that follow, and on most calculators, this compounding period is represented by the small letter n. The interest rate per compounding period is usually abbreviated by the letter I. Sometimes the interest rate is represented by the percentage symbol. Usually you have to enter the interest rate per compounding period. So, for example, if the annual interest rate is 5% and you have 4 compounding periods per year, you would enter 1.25% into your calculator. There are actually 2 ways in which the bank might pay you or credit you interest. One way they could pay you interest is simply to compute it based on the original $5,000 deposit. This is called simple interest. The more typical way banks credit interest is the compounded interest method. In the compound method, interest is credited based on the original amount of principal plus the previously credited interest. This compounding, of course, assumes that you have not withdrawn the previously credited interest earned. This table illustrates the simple and compound interest computations, assuming an interest rate of 5% compounded annually. The table shows that the amount that you would accumulate after 5 years under both methods of crediting interest to your account. So starting with $5,000 today, we would accumulate $6,381 by the end of year 5 using the compounding method versus $6,250 or $131 less using the simple interest approach. Now, almost all computations of interest involving financial instruments utilize compounding computations. So it is important to note the difference between the nominal versus effective interest rates. Usually a bank will advertise both a nominal interest rate and an effective interest rate. A nominal rate is usually a rate assuming 1 annual compounding period, but almost all banks and other financial institutions will compound interest more frequently. The relationship between the nominal and effective interest rate is described by this formula. This table shows the relationship between the nominal and effective interest rate holding the number of compounding periods constant at 12. You can see that the effective interest rate increases with increasing nominal interest rates. Now, a very interesting pattern emerges when a nominal interest rate is held constant and we greatly increase the number of compounding periods, not just within 1 year, but over several years. We also see the impact of increasing the number of compounding periods within a year. In this table, we assume $1 is put into a bank account and will earn 5% nominal interest over 20 years. Each row shows an increasing number of compounding periods per year. In the last column, you begin to see the accumulated balance get closer and closer to a very important number known as E, or Euler's constant. As the compounding periods increase, the accumulated balance will get closer and closer to 2.71828, which is to 6 significant digits, E. This constant appears in many important applications, particularly in probability and statistics. Finally, the last column of this table contains the general compound interest formula for computing the future value of a lump sum. This lump sum we have been calling the present value or initial deposit. The accumulated balance we will refer to as the future value. Again, the above formula and example assumes that all interest is reinvested and compounded. Before continuing with the mechanics and applications of present value and compound interest formulas, in the next video, I want to discuss how interest rates are established. So click here for the next video.